talk more about what we can learn about the dark matter distribution from cosmological simulations and astronomical data. So why is this important in terms of looking from the perspective of dark matter searches? Well, for direct detection searches, these searches are really strongly dependent on one of the inputs in these calculations of the rates of these searches is the dark matter distribution in the solar neighborhood. And more specifically, the local dark matter density and the local dark matter velocity distribution in the neighborhood of the sun are important inputs, which whatever uncertainty there are in these different distributions would translate to also large uncertainties when one wants to interpret the data of direct detection experiments. So to just see this in the equation of the rate, this is the differential event rate per unit detector mass in direct detection experiments. And here, V min is just the minimum dark matter speed, which comes in the limit of this integral to produce a recoil energy in the detector. And here, the two astrophysical inputs is the local dark matter density and the velocity distribution. Now, the local dark matter density is a normalization in the event rate. So we know that the direct detection limits would just shift up and down if this local dark matter density is different than what is usually assumed. But the local dark matter velocity distribution would enter through this integration, so it becomes more complicated, especially for considering the result of different experiments and comparing them. And whatever uncertainty we have on this local dark matter velocity distribution would also translate to uncertainties on the cross-section. Limits on the cross-section. And so these plots that usually you see of the dark matter Nucleon cross-section and dark matter mass, these are the limits from different experiments. And these all have a specific assumption for the dark matter velocity distribution and dark matter density. This is the so-called standard halo model, and I'll mention a bit more about that. But the point is that by changing the local dark matter density, these limits would shift up and down, and the local dark matter distribution, usually it's more complicated, but usually you'll see that it shifts towards right or left if you consider changes in the tails of the local dark matter velocity distribution. Now this becomes more important if you have some hint for a signal so that you have some region of interest somewhere here, let's say at low masses, then these can become quite important uncertainties to shift things up and down, or left and right. So what is the standard halo model? It is really the simplest model that is usually assumed for the dark matter distribution in our galaxy. And the assumption is that the dark matter is distributed in an isothermal sphere. And this leads to a velocity distribution, which is isotropic Maxwell-Boltzmann distribution. So this was introduced in the 80s. And the density profile goes as 1 over r squared, so it gives us flat rotation curves at large radii. Local dark matter density is assumed to be fixed to 0.3 GeV per centimeter cube, and the most probable dark matter speed is fixed to 220 kilometers per second. But of course, I mean, even if you assume that this model is okay, there are uncertainties in these parameters that one has to consider. And again, also the actual dark matter velocity distribution may have significant deviations from the standard halo model. So this is a nice starting point, but is this really okay? Would this work? And we wanted to try to see if we can get some information for the dark matter distribution, both from simulations and then also complement that with what we have from observations. So for the local dark matter density, we already have estimates from observations. So we weren't too concerned to find values from simulations, but from simulations, it was just checking to see if they match what we know from observations. So from observations, there are two main methods to find this local dark matter density. One is the so-called local estimates, that kinematical data from some population of stars close to the sun is used, and these measurements are usually robust, but you also have to consider the contribution of baryons, which have significant uncertainties. So usually these have large error bars. And the other way is the so-called global estimates, where you use rotation curve data, and basically you have to model the mass of both the luminous and the dark matter mass of the Milky Way, and then you fit it to rotation curve data across the galaxy. And these usually have good precision, but it's also strongly model dependent, so you have large systematic uncertainties. And over the years, we know that we have more data on this, but we know that it falls between maybe 0.2 to 0.8 GeV per centimeter cube, and there are uncertainties in these. There are some more recent local estimates, but all of these, so some of them with Gaia, but all of these are quite affected by systematic uncertainties as well. So again, as I mentioned, for direct detection, this is just a number which goes into the limits. And so we know at least that things shift up and down in the cross-section and mass plane. The velocity distribution is a bit more complicated. This, as I mentioned, depends on what you assume for your halo model. And in the standard halo model, it leads to a Maxwellian velocity distribution, but we also have to take into account the escape speed of the dark matter particles from the galaxy. So we put a cutoff usually on this, so it's a truncated Maxwellian velocity distribution. Again, there are uncertainties in these estimates and recent values for these as well. So how can we obtain information from simulations and observations about the local dark matter velocity distribution? So from simulations, what is usually done is that you go to one of these large cosmological simulations. It's better to have many halos to look at. You identify the ones which you think are Milky Way-like. Then you go to the solar position and you extract the dark matter velocity distribution from these simulations, and then you can see actually how, if you use this velocity distribution in the calculation of the event rates and expected event rates, you can, instead of what you assume for the standard halo model, you can see how these change, shift up and down or left and right, and you go to the cross-section and mass plane. From observation, actually, you can extract the dark matter component of specific stellar structures which are observed. So you can, if you have, for example, with Gaia data, there was this recent stellar population which brought in a lot of interest. This was a stellar population in radially and isotropic orbits, and we wanted to see what is the dark matter component of this structure. And then if you have some simulations and you see in these simulations this exactly or something very similar to this stellar population in the stars, in the simulation you can see what is the dark matter component of it, and then we can actually see what is the effect on direct detection. Okay? So I'm going to first talk about this part, what we can learn only from simulation. And then in the second half of the talk, I'll discuss what we learn specifically for this population of stars from both simulations and observations. So from simulations, so we have all these, we have these cosmological simulations. So this is the illustrious simulation, and you can see that these are large cosmological simulations with many particles, and now it's showing you the dark matter density. So the white is more dense areas of dark matter from times very close to the Big Bang, and you can run the simulation until today. So due to the force of gravity, you have the dark matters accumulating and producing these clumps, and the normal or ordinary matter or gas basically falls into these clumps of dark matter and then cools, and you can form galaxies. So now it's switching to ordinary matter, and these different colors that you see is just a different temperature of gas, with white being really hot gas. And you form galaxies, and you have this, at these centers, you have these supermassive black holes, which this is the heat which is radiating away from these from the matter which is accreted close to the black holes. And then if you run these simulations until today, which include all these complicated astrophysical processes, you can actually see that you form a zoo of galaxies. So this is just the ordinary matter, the luminous matter that you're seeing here, and different types of galaxies, and they are similar to what we know about our galaxies in the universe. So we wanted to go to these galaxies, and find ones which are similar to the Milky Way, and see what is the dark matter velocity distribution at the position of the sun, because there are many of these galaxies in these simulations. So this was done in 2008 with dark matter only simulations. So at that time, we didn't have all these many of these cosmological simulations which include astrophysical processes. So these were run without the effect of baryons. And what they found was for the velocity distribution, what you find from simulations is in these blue curves. They had significant deviations with respect to a Maxwellian. So there were these deficits at the peak, and these excess at high velocities. But we wanted to see if this picture changes if you include baryons, because of course there's a lot of systematic uncertainties in this sort of results, because the effect of baryons is neglected, and baryons are important, especially at the position of the sun. And so here in this plot, which is quite busy, I'm putting together all the different velocity distributions that we have from different simulations, which include now all these astrophysical processes. And they include so these are dark matter plus baryon simulations, but they have different galaxy formation models, different spatial resolution, and what is the dark matter particle mass, or the smallest size of what is called particles in these simulations, which are 10 to the 6 or 10 to the 5 solar masses. They're different, okay, so the resolution are different. And so in this plot, so a lot of these simulations actually have maybe few halos, so more than one, but I'm just showing the velocity distribution for the halo in that simulation, which is farthest from the standard halo Maxwellian, to just see what is the range of different velocity distributions you can get from all these different simulations. And we find that there's a large variation in the speed distributions between the results of these different simulations. This is the usual standard halo model in black. And these are the range of different velocity distributions we get. Of course, some of them we think maybe it's not exactly correct because of stellar masses are not correct in some of these simulations, or rotation curves are not fitting correctly. So, but this is just to show you the results, just taking the results from different simulations. Also, I think one of the important things that we found was that there are different criteria used to identify what it means by a Milky Way-like galaxy in different simulations. And usually, what most people do is to just take the galaxy which has a correct mass, more or less falls into the correct mass range of the Milky Way, as Milky Way-like, without checking other things. And then you can, produce a velocity distribution for that, and you can find what is the velocity distribution of that galaxy.
Sorry.
Yes.
In the
NIHO, yeah.
Is that one? Is it just that the halo and the baryons are moving differently, like by 200?
This is very strange. We were in touch with them to understand why this is so large.
Yeah.
I think the stellar masses are not correct.
Okay.
In those.
But it also seems like if one's just moving,
Yeah, this is in quite high rotation, right,
Yeah.
for a velocity for the, yeah. So we don't know exactly what's going wrong there, but I think for sure the stellar masses were not correct. So I'm not sure the rotation curves fit well at all.
Okay.
Sorry about
Yeah.
Nihao. I think they had quite a low star formation critical density. I think that's what.
If I had to guess, they would have very weak feedback.
Yeah, there was something about. Yeah, I think about the star formation criteria, which was quite unusual compared to the other ones from memory. So
Yeah.
I can see why that would be off. Same with Eagle, they had a problem with their feedback as well.
Yeah. So so I'll talk more about Eagle in a minute. So what we use is actually we wanted to So first of all, we wanted to see what criteria we have to use to identify these Milky Way-like galaxies. And we used the Eagle and Apostle simulations. So just to give you a little bit of detail about these simulations, Eagle is this. So it's a large cosmological simulation that the resolution that we used was the high-res Eagle, which the box that is used, the volume, has a side length of 25 megaparsec, and this is the number of particles in the box, and the mass of the gas and mass of dark matter particles. And the Apostle is zoomed-in simulations of local group analog systems, so Milky Way and Andromeda-like galaxies, and they are comparable to resolution to this Eagle high-res. So we used intermediate resolution Apostle, which is similar to Eagle high-res. And these are calibrated to reproduce the observed distribution of stellar masses and sizes of galaxies today. And the nice thing is that there are companion dark matter only simulations. So each of the halos in these hydrodynamical simulations have a dark matter only counterpart. So we can compare directly and see what is the effect of baryons for each halo. And so this is a side length. This is a picture of the gas. Now the different colors again are different temperatures in the Eagle simulations, and this is a 100 megaparsec side length. And then if you zoom in to some region and zoom in further, you see a galaxy which looks like a spiral galaxy, and this is one of these Milky Way analogues, which is the face-on and edge-on image of the same galaxy here. But how do we identify these? So we used, in addition to the mass, mass of the galaxy, which has also large uncertainties, we used rotation curve data that we have coming from this work, which was a compilation of many rotation curve data, about 2,700 data points here from all the references which had this data on rotation curves, and also the total stellar masses of these galaxies. So what you see here, this is rotation curves, but it's VC over R, so it's angular velocity, circular velocity. And these black points are the data points that we have for Milky Way's rotation curve as a function of radius from the center of the galaxy. And this magenta band, so you don't see it here, but there's actually a very light magenta band from here to here, which is actually the rotation curves compilation of all or envelope of all the rotation curves from all the halos which had the correct Milky Way mass in Eagle. And then this darker envelope is the ones which have the correct stellar mass. Okay, so putting the criteria of having the correct stellar mass was quite important, especially for Eagle, because they have this mismatch between stellar mass and halo mass. So stellar masses had to work, and also we saw that those which had the correct stellar mass also naturally fit better the rotation curve data, and this is the best fit one. So we started with initially 61 halos in Eagle, 24 in Apostle, and the ones that, based on these two criteria, we chose were 14 in total. So 12 in Eagle and 2 is still quite, number is larger than anyone else, because all the other simulations, well, they don't have this many halos, or they have a few, like 3, 4 halos. So this is quite good statistics, I think. So we could have put more and more criteria, but then we lose statistics. And we found that for direct detection, velocity distributions, and so on, having the correct rotation curves is quite important, because you want to make sure you have correct velocities at the position of the sun. And this also, see that the criteria on stellar mass was also quite important. So then we can actually, for these 14 halos, see, go to the, well, first we want to see what is the dark matter density profiles, but more importantly, so here I'm just showing you the spherically average dark matter density profiles of those halos in Eagle, and this is like an NFW profile here with some specific parameters. What we're interested in for direct detection was at the solar neighborhood. So we can go at 8 kiloparsec, and instead of taking a spherically average density profile, we consider the torus region, or just this cylindrical ring, basically, which is with some radius which is around the position of the sun, 7 to 9 kiloparsec, and this is aligned with the stellar disk, so from -1 to 1 kiloparsec in height. And we find that the dark matter density at the position of the sun agrees well with the local and global estimates that we know from observation. So that was a check that that's fine. And then we wanted to now find what is the velocity distribution in this torus of the dark matter particles. And so this is in the galactic rest frame, and this is showing you the velocity distribution for 2 different halos in Eagle. The green and the magenta, again, are 2 different halos, data points. And then what is plotted here as dashed colored curves are their best fit Maxwellian velocity distribution. So taking the Maxwellian and finding the best fit with the free peak speed or free dispersion, and seeing which one fits better. And this black one here, black curve, is just a standard halo model. So a standard halo model with this specific peak speed, 220 kilometers per second, matches one of the halos well, but there are different halos which have different velocity distributions. But they fit quite well in Maxwellian distribution. Then we can actually see what happens to their dark matter only counterparts. And we see actually they don't fit a best fit Maxwellian distribution. So we see similar results to what were published in 2008 by other simulations like Aquarius, that you have these deficits at the peak and excess at low and high speeds. And so, yeah, so Maxwellian distribution with a free peak provides a better fit to the halos in the hydrodynamical simulations compared to the dark matter only, but there is a range for the peak speed. It's not the 220 kilometers per second, and depending on the realization, right, on the halo, it can range from 220 to 290 kilometers per second based on this simulation. And we also find that from the simulations that I showed you, there are some common trends that we wanted to see if we can obtain these trends. And one is that baryons always deepen the gravitational potential in the inner halo, and we always see that they shift the peak of the dark matter distribution to higher speeds. And in most cases, baryons also appear to make the local dark matter distribution more Maxwellian.
So can I ask you a quick question? So you're looking at this torus region. Yeah. Did you compare what you get with this torus region only versus if you took a spherical shell? Does that actually make a difference?
So
Okay,
that's a good question.
Does it make a difference that you're with it, that you're in the baryons, or just that there are baryons in the simulation? I guess.
So yeah, that's a good question. I don't think we compared. We did that for the dark matter density, and it wasn't. There weren't much of a difference. The halo to halo variation was larger than any difference comparing like the spherical shell.
Right.
Well, there is like I think 30% difference if you consider the disk because of the contraction of the halo, and also the dark matter changes. The density of the dark matter also changes due to that. But this halo to halo variation was higher. For the velocity distribution, we didn't look at the shell because we wanted to really see what happens at the local position. But that's a good question to see what happened. We did look at different positions around, and there is some variation. Again, the halo to halo variation is higher. So different azimuthal angles. So we look at the different sections of the torus and see if there's some transient effect there. But
then you run into statistics as well.
Right, you lose statistics, yeah.
But the velocity distribution is isotropic, so the particles aren't living in the shell, or in the ring. I mean, their velocity, you know, the ones that you happen to find in the ring.
Presumably, yeah.
But
It's good, yeah, it's
it's
interesting to
interesting.
check.
I'd be
Yeah, yeah.
They're
good
not
if they're.
perfectly isotropic though.
Well, if it's becoming more Maxwellian.
Yeah, they become more Maxwellian compared to the dark matter only.
Yeah.
And just to understand a little bit why this is more Maxwellian, or basically looking at rotation curves and seeing what happens there. So you see for the dark matter only rotation curves, halos, so it's this red, around 8 kiloparsec, they're still rising and they haven't really reached the plateau, flat rotation curves yet. Whereas for the hydro halos, they're already at 8 kiloparsec, they're close to isothermal. And you can, because also you have reached this plateau here in the rotation curves, you can also compare the local circular speed to the peak speed of the isotropic velocity distribution. And isothermal is when these are equal. And so you see that the hydro halos are closer to isothermal. So this circular speed is higher, again at 8 kiloparsec. So this is at 8 kiloparsec again. It's higher at 8 kiloparsec, again, due to the deepening of the gravitational potential. So we can see that things are not exactly isothermal, but they're closer to isothermal when you include baryons due to the deeper gravitational potential. So now what happens to the direct detection event rate? As I mentioned, there is the local dark matter density and velocity distribution here. And we can actually simplify this a little bit more if we assume standard spin-dependent or spin-independent interactions. This cross-section has a 1 over v squared dependence. And so all the v dependence in this integral can be written in terms of this integration, or this so-called halo integral, so you have to take your velocity distribution from the galactic frame to the detector reference frame, but then you have to integrate it over all these velocities larger than your minimum dark matter speed, and then your rate becomes basically proportional to your astrophysical contribution, which is from this halo integral times the local dark matter density. So this is what we wanted to plot. So it's really that we're not directly sensitive to F, but what we have to look at is just the halo integrals to see how the direct detection limits change. And so this is the halo integral as a function of V min for the same two halos. So what you see here is with the 1 sigma uncertainty band of, this is one halo and this is the other halo. The black is the standard halo model, halo integral, and the dashed colored curves are the best fit Maxwellian halo integrals, which analytically you find the best fit Maxwellian and you analytically find the halo integrals and plot them, and you see that the best fit Maxwellian halo integrals fall within the 1 sigma uncertainty band of the halo integrals of the simulated halos. So it seems for direct detection, even there were some changes. Some of these halos had velocity distributions which were different, a little bit different at some velocities. compared to their best fit Maxwellian. But when you go to halo integrals and you look at all of the 14 halos, all of them show this result. Okay? Whereas if you look at their dark matter only counterparts, there are large differences between the best fit Maxwellian halo integrals and the ones you find from simulations at large speeds. So again, and because you have this shift of the tails of the halo integrals to higher velocities in the case where you include baryons. And so this is quite interesting because there were also these two other results of two other simulations, MAGIC and another one, which came out around the time that our work came out, and they found the same thing, that whenever you are including baryons in the simulations, things become more Maxwellian, and compared to when you have dark matter only. So we can look at what happens to these constraints. So this was just to show you, because we only had gamma for some region, just to show you what happens if you have some allowed region, let's say, into it. But these have been already excluded by, so for spin independent, just looking at the DAMA data itself excludes its results. So anyway, we don't consider it. But just to see how things change. And so we see with our halos, considering the simulated Milky Way-like halos, the same two halos that I showed you, we find a factor of 2 to 3 shift in cross-section, which is due to the change in the local dark matter density. And we have a few GeV shift in mass at low dark matter masses. And this is just due to the velocity distribution. And to see this better, we can compare, actually, this is the same plot I showed you before, to fixing the local dark matter density of all the halos to 0.3. This is in principle not consistent to do it, because if you change the local dark matter density, you're also changing the velocity distribution. So density and velocities are correlated, but let's, just to see by eye, this is not correct completely, but just to see by eye what is the effect of the velocity distribution, we see that there is this shift in the low mass region, and this is because the experiments, when you have these changes, you saw these changes in the halo integral at the high velocity tails of the halo integral, and this is larger V min, and this is where the experiments are probing low dark matter masses. So large V min means low dark matter mass, and that's why this shifts to this, translates to this shift at low dark matter masses. And this is comparing to the other two simulations, MAGIC and this other one from Sloan et al. And again, fixing the local dark matter density, depending on their best fit peak speeds that they find for the velocity distribution, there is some shift in the exclusion limits at low dark matter masses. How general are these results? What happens if you consider non-standard interactions? Because what I mentioned about the halo integral was only for when the cross-section had this 1/v² dependence. But for a very general set of non-relativistic effective operators, you can always write the cross-section as a linear combination of a term which has a 1/v² dependence and a term which doesn't have any velocity dependence. And so this first one gave rise to the usual halo integral, which I showed you. And the second term gives rise to a different velocity integral. So this we saw that it matches quite well the best fit Maxwellian, and we can actually check it for this term, and we see that the results are similar. So this is this h as a function of V min, and again, the best fit Maxwellian falls within the 1 sigma uncertainty band. Actually, there's a relationship between these two as well. So in any case, seems quite general, these sorts of results for how these velocity distributions compare to their best fit Maxwellians from the simulations. But what happens now if you have some substructures there? And so we wanted to see if there are some inputs that we can use from observations. And so Well, of course, we have now Gaia, and really Gaia provides this unprecedented level of information about the galaxy. And so we can definitely see what happens in stars around the position of the sun, and if we can actually find out what happens in dark matter, which are related to those stars. So we specifically looked at this structure, which was called originally the sausage, Gaia sausage, which we didn't like that much. So we are calling it GRASP, Gaia radially anisotropic stellar population. So it's a prominent population of stars in the inner halo, and these stars have really high radial velocity and isotropy. So they're on really high radial orbits with high anisotropy. And then there were some simulations around the time that this came out, which showed that this GRASP structure originated from a massive dwarf galaxy, which was on a radial orbit and merged with the Milky Way about 10 gigayears ago. So I'm just learning from Larry that there are some groups looking into this again, and maybe it was later than 10 gigayears ago. So in any case, we have this structure now in stars, and this is how it looks in the velocity space. So this is azimuthal velocity, and this is radial velocity on the x-axis. And this is a complicated slide, but this is just how this is with 1 to 10 kiloparsec from the sun, and the SDSS and Gaia data, how the local stellar halo looks close to the position of the sun. And you see that here, if you look in this, so we are increasing metallicity in this way and increasing galactic height here. So this is close to the disk of the galaxy. And you see two populations, and this is metal-rich stars. You see two populations. This is the disk, which is rotating at 200 kilometers per second, and it doesn't have much of a radial anisotropy. Whereas there's this other population, which is not rotating much, but it has this big radial velocity and isotropy. Okay? And if you go up from the disk, you're losing the disk, you don't see it anymore, but you still have this radial and isotropic population. And here the error bars are increasing, so that's why things become more fuzzy, but you still have this here. Whereas if you go to metal poor stars, you don't see, so you have an isotropic population there. So this is in more metal-rich stars that this radially anisotropic structure exists. So these are all in stars, and we wanted to know if around the position of the sun you have this high radial anisotropy stellar population, well, that might actually change your velocity distribution because you might have a component of dark matter which also has this high radial velocity and isotropy, and then this might change all these Maxwellian results that we have found. And there are actually a lot of interests in this, and a lot of a few papers which pointed that this can significantly change everything. So we wanted to see what are the properties of the dark matter component. I think these two were two of the original papers which looked into this. And they model the dark matter velocity distribution of this GRASP. So by looking into fire simulation, so this is another hydrodynamical simulation, they find that old metal poor stars trace the dark matter which is accreted from the oldest luminous mergers, and intermediate metallicity stars trace the dark matter accreted from younger mergers. So then they say that they can go to, based on this tracing of the dark matter by the stars, they can go to Gaia data, and they can extract what is the stellar distributions of all these two different populations, and they can build a dark matter distribution based on the stellar distributions. And this is the result that they find. So this is the standard halo model here, and this is the velocity distribution that they infer basically based on what they find in the fire simulations. There is a subtlety here. And this is that actually, this is only tracing of the dark matter from luminous mergers. And so the issue is that a non-negligible part of the local dark matter halo comes from smooth accretion as well as dark substructures, which you cannot do with this method. So you cannot just go to data and take from what the stars do and say this is the full dark matter. So direct detection experiments are sensitive to the total dark matter distribution. They cannot find out which part came from luminous mergers and which part came from just dark substructures. So this has to be taken into account in a way, and this becomes more difficult. There was another work which models this dark matter velocity distribution based on the basically what we know from the density of the stars that it falls with as 1/r². If the dark matter density also follows that, then to solve the Boltzmann equation, you can consider velocity distribution, which is a combination of a Maxwellian plus an anisotropic velocity distribution. And an anisotropic velocity distribution is in this form, where beta is just the anisotropy parameter. And so they introduced these SHM++, which if you have the standard halo model and you add, let's say, 20% this sausage structure to it, what happens to the standard halo model? And this is the different fraction of this structure that you assume. The issue here is that you have to make assumptions for this. So for the fraction of dark matter in this sausage, there are some arguments because this cannot be too high. It really cannot be more than 20 or 30%. Otherwise, it would change rotation curves. It would change the ellipticity of the disk. It would change kinematics of stars. So we would have noticed that. But for the anisotropy of this dark matter, so this is the dark matter anisotropy parameter, they set it equal to the anisotropy of the stars. Okay, and we wanted to see if this is fine in simulations. What does a simulation of galaxy formation tell us about this? So we have results of simulations. Now these are really state-of-the-art simulations called Auriga. These are magneto-hydrodynamical zoom simulations of Milky Way size halos, and there are 30 halos at the standard resolution there. And the nice thing is that the work which was done on these simulations, so these were already run, and you have the halos, the 30 halos, which have the mass of the Milky Way, and they found actually that 10 of these halos have this grasp structure due to some mergers. So this was after simulations were run, they did this analysis and found that 10 of these halos have this structure. And actually, this is one of the simulated stellar halos in one of these halos. And this is very similar to what I showed you before. They're not including the disk here, so you don't see that disk. But they see this anisotropic structure in stars. And so, yeah.
How local is this?
This is 5 to 20 kiloparsec from the galactic center. So the previous one was 1 to 10.
But I mean, how large is this particular structure of stars that you see? Is it like a blob?
Yeah, so this is, the structure actually is all through the disk.
Throughout the entire disk?
Yeah, the entire disk, there are these radially anisotropic. And you saw that as you go up the disk also, it still was there. So you have it close to the sun, it's there in stars. And yeah, so we wanted to actually go to some of these halos, these 10 halos, and see, well, we have this in stars, we can automatically see what is the dark matter distribution. And so again, we wanted to identify it not just by mass, but by the fit to rotation curves and stellar masses. So from these 10 halos, which have this grasp, we had from 30 halos, 10 of them were Milky Way-like by our criteria, and 4 of them have the grasp. So we still have 4 halos we can work with. And what we find, if again we go to this torus region, we find that depending on the halo, there is a range in this fraction of dark matter in the grasp. So this is still, we agree with this results of Evans et al. That it cannot be so large. So the largest is 17%. But the interesting thing is that the anisotropy parameter here, it's never reaches 0.9, but it's a range between 0.5, let's say, to 0.8. And what we also found was that something which goes against having a big effect for direct detection was that the larger the anisotropy, so the larger the fraction of this grasp, the lower the anisotropy parameter of it. And so this is all of the grasp-like halos here, and the red are the 4 Milky Way-like halos with the grasp. And so the reason of this anti-correlation can be quite complicated to understand. There are still some ongoing studies that we're trying to understand it, but this comes from 2 other correlations. One is this beta parameter, or the anisotropy, is also correlated with the dark matter mass of the grasp progenitors at infall. And also this fraction is correlated with this dark matter mass. This is quite standard, so you have a higher fraction if you have a higher dark matter mass, progenitor mass at infall. But this one can be quite complicated. It's really an interplay between tidal stripping, the dynamical friction, and also dependence of the orbital parameters on subhalo mass at infall. So one has to really trace back in time the orbits of these particles and see where they come from and why the more radially anisotropic ones come from larger dark matter progenitors. But for us, we just note that this anti-correlation exists, and we can actually use this to see what's happened with the velocity distributions. We also looked at the local dark matter densities of these halos, and well, first of all, it doesn't have the 1/r cubed as the stars. It doesn't have to have this sort of profile. This is all dark matter, and for the 4 halos, the profiles are very similar, but when you look at the dark matter in grasp, depending on the halo, it can be quite different. This is for the one which has really small number of particles which are in the grasp. And so there is this difference between them. The local dark matter densities, again, there's no significant difference between the values for the halos which have the grasp and those which don't have the grasp. And there's a range, again, which matches the global and local estimates, so there's nothing significant there with the effect of the grasp. So the ones which have the star is the 4 which have this grasp structure. And then for what happens with the speed distributions, so this is comparing a halo which doesn't have this grasp structure, and the black is the hydrodynamical dark matter velocity distribution, and the dashed is their best fit Maxwellian. And just to compare with the dark matter only, again, the dark matter only doesn't fit the best fit Maxwellian, so the result is similar to all the previous results. And there's a shift to larger speeds for the hydro halo. And if you compare it with a halo with grasp, the only difference is that we see that the fit becomes worse for the best fit Maxwellian. But we checked what Evans et al. Introduced to have 2 components, Maxwellian plus anisotropic, and it doesn't fit better than the usual Maxwellian. Again, because of this anti-correlation we have between the fraction and the anisotropy of these grasp particles. So this doesn't fit. But we found that if we add a parameter to this Maxwellian, this is the generalized Maxwellian, which has this added parameter alpha, the fits become better. So this is the screen line, which is just the best fit generalized Maxwellian. So this fits a bit better due to the extra parameter, although here there was an extra parameter, but it didn't fit better because, again, these anisotropies are quite low for the ones which have a high fraction. And if you remember, you have to consider the fraction here. So this was the fraction here. So the ones which have a high fraction have a low anisotropy, so this doesn't work. Okay, so we can compare it with the standard halo model, and this is all the halos. I'm just putting it here together. The halos without the grasp, and this is the halos with the grasp, and this is the standard halo model. And so the ones which have the grasp are shifted to higher speeds compared to standard halo model. But there is a large halo-to-halo variations for halos without the grass because you have more of them here. So we have 6 halos without the grass, and so there is a large halo-to-halo variations here. We have only 4. And again, we can look what happens to these halos in terms of them being isothermal. And the ones which, well, the DMO ones are quite far from isothermal. The ones without grasp are quite close to the isothermal. And when you add the grasp, they become a little bit different than isothermal, still much closer to isothermal than dark matter only. And then the important part for us was not the velocity distribution, but this halo integrals, which is directly proportional to the event rate. And we see that actually this is one halo without the grass, and so we have very low error band here because of the resolution is quite good. And so the best fit Maxwellian more or less works, whereas here the best fit Maxwellian tails doesn't fit quite well the halo integral, but when you do a generalized Maxwellian, it becomes closer to that. And we looked for the 4, and it's a similar result. So generalized Maxwellian agrees well with these halo integrals. If you're looking for a functional form to try to understand this is the next best that one can do. But of course, we can just use directly these simulation data, not to use a fit, but use directly the simulation data to do the analysis of direct detection. Well, before that, just to show you for all the halos, how these look compared to the standard halo model. This is without grass, this is with grass. And here you see that, again, we have a larger halo-to-halo variation compared to this one. But here there is a little bit of excess at the tails compared to the standard halo model. And so we wanted to check direct detection limits. And so we wanted to look at 2 future detectors. So we simulated the signal into idealized germanium and xenon detectors. And for the germanium detector, we used 2 different designs, which is similar to the CDMS or super CDMS designs. So a low threshold design, which is sensitive to low dark matter masses, and a high threshold but low background design, which can actually go to larger exposures. And these are achievable by super CDMS after 5 years of operation by 2024. And also an LZ detector, well, similar to an LZ detector, so a xenon-based detector. And this can be reached around the same time. And so this is the result of the direct detection limits. So again, the black, which you see here, this is the top line here, is the standard halo model. And all these colored lines, so this is for germanium, this is for xenon, the different colors are the different halos here. So it's a very slight change, and this is due to the different dark matter densities, local dark matter densities. Again, we fix the local dark matter densities, and everything becomes very similar to the standard halo model. So all these claims that there's this large shift at low masses, actually with these halos, we don't see that. And this is the ratio of the change in the cross-section for these Auriga halos compared to the standard halo model. And if you look at the grasp one, the ones without the grasp, actually there's a bigger halo-to-halo variation, so there's a bigger change. So considering all the halo-to-halo variations, actually the grasp is not actually producing much of a difference. So it's a mild shift at low dark matter masses. So this is just side by side the one when you fix the local dark matter density, and you compare halos with the grasp with halos without the grasp. And so there's a larger halo-to-halo variations for halos without the grasp because there are more halos there. And you have a mild shift of the exclusion limits for halos with the grasp towards smaller dark matter masses compared to the standard halo model. Okay, this brings me to the conclusions. So simulations and observations can really provide insight regarding the dark matter halo at our local positions. In simulations, we need to identify the galaxies which fit Milky Way kinematical data. And what we find from the recent simulations is that the local dark matter density agrees with the local and global estimates, and the Maxwellian velocity distribution in general seems to be working well. So experimentalists can still use this form, but there is an uncertainty in the best fit peak speeds, which comes from the different simulations. So it's not the 220 standard halo model, but it's an isotropic Maxwellian with some variation in the peak speed that one has to consider. If you consider observations as well, we studied this dark matter component of this grasp in Auriga, Milky Way-like halos, and we find that the fraction of the dark matter particles is between 0.6% to 17%, the ones that belong to the grasp, and the anisotropy can range between 0.48 to 0.82. Best fit generalized Maxwellian works well if you want to be really precise about these halos which have this grasp. So this does change this, what we can take as the functional form if you want to find the functional form with some parameters. But all of this produces a mild effect on direct detection limits for light dark matter. So this becomes again more important if you have some detection, especially for these light dark matter, and you want to really pinpoint the particle physics, the mass and cross section of these particles, then it's important to know better. And I think with better simulations and better data, I guess we could know all these uncertainties. We can reduce them more and know better exactly what is the form of this velocity distribution. Thank you.
Questions for Nassim?
Mine wasn't that good, so.
All right, go for it.
Is there a physics motivation for the generalized Maxwellian?
No, that's a good question. You might think that, well, it doesn't, it's quite difficult to think of a physics motivation because it's not, it might, and we think it's not steady state with all these different substructures there. So it's not going to, satisfy the Boltzmann equation or steady state Boltzmann equation. So yeah, why generalized Maxwellian is just a functional form which works.
Thank you.
All right.
It almost seems like if we were to ever detect dark matter and have a really accurate speed or energy distribution, we could use that to probe feedback and dissipation in dark matter. As opposed to, I mean, the other way, it almost seems like it's a probe of whether the simulations have the physics right. As you were saying, the outliers are probably because the simulations had something wrong in their
there's
feedback
always
scheme.
the question of how good are these simulations and is this realistic. So that's why I think we have to look at different simulations which have all these different baryonic feedback. And it was interesting for us that all the other two simulations which did this study found something very similar. So the ones before that were maybe more earlier simulations which maybe didn't have the resolution, as well as these more recent simulations, which like this the few that I showed in that plot. But the ones which did look into halo integrals, they find the more recent simulations, they find that things become more Maxwellian with baryons. So it's at least I think it's a nice thing that's different. It's not so sensitive to the baryons, specific baryonic feedback or the resolution that they're using. But it's definitely, it would be quite interesting, although I don't know if we will ever reach that, to go to data from direct detection if there is some signal and try to go back to, if you have so precise signals, to try to go back to reconstructing the velocity.
Dark matter astronomy.
Yeah.
Right, but it's an interesting point that the component that has no thermodynamic relaxation in it, it's just gravity, is somehow relaxing because it's coupling to something that is thermodynamically. There's some statistical mechanics thing that we're not understanding fully, I think.
Related question to that. So I'm curious about, like, so by putting in the baryons, you're getting this relaxation. Is it sensitive to what the mass of your dark matter particle is? Is it sensitive to the softening in your dark matter? Is for example, like illustrious has kiloparsec scale.
Right, so we didn't, so,
softening.
yeah, so with illustrious is quite difficult we didn't use it because of the resolution. We used the Eagle, which had, well, good enough resolution to do this sort
I'm
of
pretty sure
studies.
Eagle also has a kiloparsec
Yeah,
softening. for
yeah,
the
but
amount of
so then
particles.
we used a high resolution one, which had, I think, 0.3 or 0.4, if I'm not wrong. But it wasn't too sensitive, so we see the similar thing in Auriga, let's say, which has higher resolution than Eagle. The masses are 10 times better than Eagle mass of particles. And we see actually similar results. Everything becomes more Maxwellian, not considering the grasp, just in general, halos become more Maxwellian compared to the dark matter only. So it's not too, and also these other simulations, I think Fire has better, a bit better resolution than us. And Magic, similar resolution, they found that it becomes more Maxwellian as well. So yeah, I don't think it's a resolution dependent. Well, there might be always something under the resolution of these simulations which can change things, but then, yeah, we can't answer that question. But in general, I don't think with the resolution of the current simulations it's going to change this by much.
Oh, might as well. So as we get closer to the nuclear floor, we might have to look at more directional sort of detection. Does this substructure thing make that more complicated or actually make it more interesting?
Yeah, so I think there was one study with the group of Evans and McCabe and all. They did this study of how this sausage changed this directional signature, and it does change directional signatures. It's quite difficult to measure these, right? So these needs many events to be measured, but it does. So we have this specific structure called a ring, which forms depending on the mass of the dark matter particle and the recoil energy in this. So the things are not pointed towards the average dark matter velocity, but it's in a ring around it, and this ring distorts based on the sausage. And there are all these other different directional effects. It's just that we don't have now the experiments to measure it.